So F2 is expressed as, using this expression here, is a function of F0 and F1, which is the string ABC, and so on and so forth. So I encourage you folks to take a moment to think through the problem and look and try out a few examples before diving into the solution or possible solutions. So let's, as usual, start off with a simple approach. Think of it as a brute force. So what you could do is you can basically you can compute Fn, and you could just return Fn of k. That's conditional on whether k is greater than or less than or equal to the length of Fn. So let's take this and approach and come up with a pseudocode. So I'm just going to put down a very simple pseudocode here. You have a function f. I can call it. I'm just calling it f for now. So the base case is if n is 0, you would return a. If n is 1, you would return bc. Else, what you do is you would return Fn minus 2, concatenated with f of n minus 1. And so this is a helper function, and let's see how that gets invoked. And say you have another function, let's call it foo, which takes in a parameter n and another parameter k. So you have string s is f of n, and you can say, okay, if k is greater than s dot length, and you return null, or you'd say, yeah, you could just return null, or you could return else, return s of k. So that's the s of k minus 1, because arrays are based off of index 0. So this is a simple approach. Now there are a couple of drawbacks here, so let's think through those. So the first drawback that comes to mind is f of n can grow it can grow exponentially. So your or your space complexity is not optimal, right? So, and you're not leveraging, you're not using k when generating f of n. So that can be a problem. Basically, you're considering parts of strings that are not going to be useful, because if, especially if you have a string that's much larger than k, and you're looking at, and if you're generating characters greater than, or if you're generating strings that have length much greater than k. So see if you can leverage that. And here you're not using memoization, which is you end up recomputing the solution to the subproblems over and over again. So you got to leverage some of that. So given these drawbacks of approach 1, let's think about approach 2, or another approach that may be better, a bit more optimal. Now this approach requires us to think about say, exploiting patterns that you would see in the examples that we had jotted down, that I jotted down here at the start. So let's take a look at how each of these are composed. So as you can see, f of 2. Let's start with f of 2. It's a combination of it's got one f0 in it, and it's also got one f1 in it. F3's got one f0. It's got two f1s. F4 has got, let's see, one, two, it's got two f0s and three f1s in it. F5's got three f0s and five f1s in it. And this one has got f6. It's got five f0s. As you can see, I'm deriving these rather than actually counting the counting f0s in the string, because there is a pattern to this as well. Now, the interesting pattern here is that the number of f0s is actually, or the number of f1s for that matter, it's in turn a Fibonacci series. As you can see here, f6, it's got five f0s. That's because it's got three f0s in f5, and it's got two f0s in f4. So you add 3 plus 2, you get 5. Similarly, f1, you add 3 plus 5, you get 8. So that's the observation that you come across with. And then why is this useful? Because let's take a look at the total length of each of these f2s. So this has a length of 3. This has a length of 5. This has a length, oh, yeah, let me put it this way. Length of 5, this has a length of 8. And this string has a length of should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. And this string has a length of 21. So if you observe that the lengths are also Fibonacci series here. So that gives you a pattern that you can exploit, right? So essentially, if there is a way for you to leverage some of these patterns, that then it can help us address some of the drawbacks of approach 1. So let's say let's look at it this way. So if you have k, so if you have, let's say somehow you have all of these lengths. Now, if you're given f of n, and if there's a way for you to compute the length of f of n, then you can compare that against k to decide, okay, if f of n is greater than k, then you know that, well, let's step back a bit. So let's say you have f of n, and that is composed of the function of f of n minus 2 and f of n minus 1. Now, if you know for a fact that k is less than the length of f of n minus 2, then you can further recurse on f of n minus 2 to get the character at position k. If it is the case where k is greater than fn minus 2, this means you have to look in fn minus 1, right? So which means you have to recurse on fn minus 1, and you got to look for, so you have to offset k accordingly, so which is, the offset would be k minus length of Fn minus 2. Alright, so this would be the offset, and this would be the subproblem you're interested in. So given this insight, well, this obviously assumes that you have already pre-computed these lengths so that you can look up in big O n, or big O 1 time. And so that's where this observation that we just looked at, the lengths, come into play. So if you're given f of n, you can use that. You could use this observation here to compute what the length of f of n would be. So the length of f of n again is a recursion. You can express that as a recursion, which is length of f of n is length of Fn minus 2 plus length of Fn minus 1. So you pre-compute the lengths, and then given that, we can write down first 2, which is the following. So let's call this function got string f, let's take in input n, and you got another input k. So let's just handle the base cases here. If n is 0, and if then you would return a. If n is 1, well, actually n is 0 and k is 0, return a. If n is 1 and k is 0, you return b. If n is 1 and k is 1, you return c. Now, here comes the part where we leverage, compare the lengths of Fn and k. So if k is less than or equal to, let's say you have another function, say length L of n. So let's say you have an array L that you pre-computed all the lengths of various fn's. Then you would return f of n minus 2. I apologize, this has to be k is less than, you're looking at length of n minus 2. Then you return. So basically this means on the first, if it's contained, if k is less than the length of Fn minus 2, then you only need to focus on Fn minus 2 and look for the k character in there. Else, you would have to look in the second term of the expression, which is you'd have to go look into n minus 1, and you need to adjust your offset in n minus 1 by k minus L of n minus 2. So fundamentally the idea is that